All right, we're going to start on time because we have a lot of presenters and not a lot of time. So I'm going to skip through my slides for the most part. First of all, just wanted to thank everyone who participated in this hackathon. This is the first hackathon we've done in person with RISC-V International. It was a great opportunity to provide the students with real-world problems, and they came up with solutions. So the idea came from the Academic and Training Special Interest Group. We had 25 students participate. It was only 4.5 hours. They did have time afterwards to create their presentations. They did still have access to Codicip's online platform, as well as their Renaissance hardware that they were given to take home. And I'll show you really quickly. So these are the problems. So Codicip provided a problem. The need was to optimize the neural network inference. So I'll let you read the rest of it again. We don't have a whole lot of time. And then Renaissance, their goal was to demonstrate a proof of concept by extending processor functionality with add-on sensors and communication modules. So with that, I will leave it there, and I will let the presenters jump in from there.
Hello, everyone. Thank you for the introduction. I thought we have a little bit more time, so I think I will skip again, as Megan did, the introduction about the problem we need to solve. As she said, we have to optimize a neural network using the Codicip tool. So I will not go into the detail of what a neural network is. And basically needed in the different layer that we have to choose to implement it. But I will concentrate a little bit on the operation that we need to accelerate, which are the one of the inner layer, hidden layer of the neural network, which were basically multiplication, vector addition with the biases and the weight, and the application of activation function like the ReLO to introduce the non-linearity of the neural network. So these were the functions that we were given, and as we can see, there were 2 layers that were implementing the function I just mentioned. And we can concentrate a little bit on the method that we need to use in order to accelerate the function, which was exploiting Codicip tool and in particular the Codal language in order to have a complete description of a processor and introduce a new custom instruction that was easily introduced in the system and compiled with the SDK. So we had a RISC-V 5-stage in order core processor with a base integer instruction set without any extension, and the entire system was compiled with an O3 optimization level, achieving a number of instructions that was, for everyone, the beginning, 22,646. So the method consists in defining with macros the different opcode for the new instruction and adding the different instruction to the complete instruction set architecture of the core, and recompile each time a new instruction is added the AEI simulation, which is an architectural model and not an RTL model, because of course in 4 hours we don't have the time to simulate all the RTL. And what I have done in order to improve the performance of the system was, first of all, added the multiplication instruction, because since we were using the common HISA and not the one with the extension, adding the multiplication was the first greater improvement that we can add, achieving a speed up of almost the 85% with respect to the original version. Then I concentrate on the 2 conditional checks that were present in the 2 nonlinear functions, achieving a little bit more of speed up that was about the 86%, reducing the number of instructions of about 400. And the fourth instruction that was introduced was the MEC operation, because having different multiplication inside the system and having therefore the need to access the different coefficients of the multiplication, there was many operations that required this kind of operation. I have not the time to do optimization at a further level, but one possible improvement considering the length of the inputs, so the inputs, the weights, and the bias, they all can be represented on just 8-bit. And so the one possibility was to combine each of these values and perform like a vectorization of the operation, And I mean, therefore, for multiplication at a time, I didn't have the time to look at it, but of course, it would be a more precise implementation, because if we want to make keep the flexibility of the solution, we need to consider that the input should be on 32-bit. So this could be a possible improvement just for the specific application that we were given. So thank you for the organization, and thank you to let us the opportunity to participate. Thanks.
Thank you. So, yeah, thank you again for the opportunity to present here. My name is Jan-Erik Schäfrich, and yeah, I will present my solution. So we were given a neural network, and which basically, inference, which consists of mainly of matrix multiplications, and so the operations that were performed basically look like this. So you have the input matrix and then the weight matrix, which are multiplied to generate a temporary result, which then the bias is added. We use a ReLU as an activation function, and then we go to the second layer and do that again. And at the end, there will be an output. And this is done for 16 times. And in the base implementation, it takes 23,000 cycles. And so, and the code that's mostly run is basically this nested for loop, which performs the matrix multiplication. So that's where we would spend most of our cycles. So knowing that, I've decided to accelerate, especially so the matrix multiplication is basically multiply and then accumulate operation. So, and knowing that we only got a base RISC-V core that doesn't support multiplication and MAC operations natively, I decided to implement those as the first instructions. They're basically defined like this. Then we had to rebuild the SDK for the updated process model. We compiled with O3, and the compiler picked up the instructions and no-code changes were necessary. And with that, I achieved already an improvement of 8 times, so the cycle count reduced. And then the next thing I attempted was to create or vectorize this multiply accumulate operation for layer 1, because if we take a look at the inputs and the weights, we can observe that they right now take up 32-bit for each value. So that means we use the whole register to for the operations. But actually, the input is only needs for the representation 1 bit, and all the weights can be represented by 8 bits. So we could actually perform or pack 4 8-bit values into a register and perform vector operations. The operations, and thereby we could basically perform 7 operations and then store the output. The vectorized code then basically, or if I want to describe the operation in Coda, that would look something like this. So we have we define our signals, and then I extract for the first integer the lowest 8th bit, and then the next 8-bit and the next 8-bit and the next bit, and in the end all values are summed up and assigned to the output. In order for this operation to yield the right results, I changed or had to change the input representation. So I change the representation so that all 8-bit values would fit into a 32-bit register. Basically transformed it like that. And and also for this time to that the new instruction could be used, it was necessary to use inline assembly, so I changed the code here again. And that's basically where the input and rate matrix and the output matrix are matched. And this, in the end, then yielded a result of 10 times reduction of the cycle count. And this is my final result. So, thank you for your attention and the opportunity.
Yeah, my name is Arnór, and I want to show you what I did at the hackathon. I also did the Coda zip, and I'm just going to make it quick because we had two very good introductions to the problem. So here's the initial code as we have seen, and as we saw also from the previous presentations, it's mainly the matrix multiplication that is like, at least initially, is the heaviest operation. So it makes sense to see how you can improve on that. And so what you can do here is, if you extract the indices, and you see that we have here an opportunity for a MAC operation, a multiply accumulate operation. And this is how it looks like in Codal. So S1 and S2 correspond to the two input registers, and S3 is the output register that we write to. This I was quite impressed and a bit surprised to see that when you regenerate the SDK, that the resulting compiler picks up on this. And you could see it both by looking into the assembly or the disassembled, but also on the cycle count, because it went from like an initial 22,000 something down to 2,664. Yeah, so I was impressed. And then what I did was, so it's actually not a matrix, but it's like a matrix vector multiplication that we're doing. So that means that we only need like 2 for loops. So I rewrote it, and another trick that I saw was that you can, instead of giving it like an empty output buffer, you can just give it the bias vector, which we want to add to anyway. So with this, I was able to bring it down to 2,616. Yeah, and that's what I did. I didn't go any further with vectorized instructions or anything. But yeah, so thank you. And
all right, hi everyone, I'm Yannis, and I'm going to present to you my approach for optimizing a statistical algorithm using hardware-software co-design methods. So we've already introduced the problem, so I'm just going to gloss over that quickly. The most important part is that the initial software implementation took roughly 20,000 cycles, and we're going to see that number go down quite a bit. This code doesn't tell you much other than that it's a lot. Essentially, it's implementing a multi-layer perceptron, which implements a sort of binary counter. So how could we optimize this? You've seen some approaches already. We could implement a multiply accumulate instruction. Maybe we could extend the instruction set with some other DSP-like instructions. We could try to implement some sort of SIMD architecture. We could go further and try to maybe implement an entire matrix multiplication. Those are all valid approaches, but I'm more of a hardware person, so I took a different approach. I took this entire code and simplified it into a single instruction. 30 lines of C code to a single assembly instruction, that's quite a reduction. I implemented this in CodaSIP's Codal language. Essentially, this implementation is rather long, so I'm just going to focus on a short part, which I had a lot of fun debugging. Any ideas what could be wrong with this code? Took me around 3 hours to figure this out. Okay, I think then I'm just going to tell you. The issue is with this load val instruction, which executes a load word from memory. The issue is it's expecting an address, not a pointer. The codal language only works with addresses, and I'm incrementing this address by single values. So the address at some point isn't aligned anymore to the word boundary, and that causes the processor to just hang. Yeah, not a lot of fun debugging. This is what I learned. Yeah, it would have been nice to have some more diagnostics when the processor crashes, because it just hangs and it's impossible to debug. But if we solve this, then the implementation sort of works. You've seen some other implementations already. They were at 3,000, 2,000 cycles, so this is a bit disappointing. So I started looking further. This was the initial software implementation I had. Can you see any issues with this? I couldn't. I had to look at the assembly. What CLang does in this case is, because model is in the scope of the function and it's not const, it assumes that this instruction can modify it in any way. So it takes the global data and copies it into the current stack frame with a mem copy, and that takes the majority of the cycles. If we optimize that out by making it global const, we're down to 48 cycles. So we could stop here, but I decided to look further. This is the generated assembly code. The top two and bottom two instructions are part of the benchmarking code. There's this branch in here for some reason. This is the corresponding C code. I don't know what this while loop does. If you could tell me later, that would be great. But the cycle count never goes above this number, so I decided to just remove it. And with that, we've shaved off another 16 cycles. So I'm pretty sure this is the lowest you can go, because the instruction to store the current number of cycles also takes one cycle, and there's 16 iterations. All right, so what did I learn from this? The most important part is to know what you're optimizing for. We were told to optimize the cycle count, not the runtime, not the area. So that's what I did. Obviously, this implementation isn't actually practical, because if you would implement this with combinatorial logic, the area would be huge. You would have a terrible critical path, and you'd have to slow down your entire processor for that. However, you could implement it with sequential logic, which would make it slower and, in practice, take more cycles. But then, in turn, you could take this whole block, implement it as a coprocessor, and kind of like we have DMA engines, let it run over the data that's in memory while your actual heart does something else. All right, I presume we don't have time for questions, so that'll be it for me. Thank you.
My solution is definitely not as efficient as the previous one. So the initial state, like everybody before me already mentioned, was around 20,000 cycles, and I managed to get it to a little bit over 2,000. My modifications were adding 3 custom instructions. I simplified the index calculation, and I removed some redundant initializations. So my approach was, first, let's identify what the common operations are and try to get those to happen in less cycles. Remove the redundant operations, of course. And simplification of index calculation happened as both a mix of identifying the frequent operations and the software optimizations. Having the most frequent operations turned into custom operations was the most efficient process so far. The heaviest one was the matrix multiplication, of course. So I just turned all of these 3 operations, the matrix multiplication step and the ReLU function and the vector step one. All of those became their own custom instructions. And that got us to 2,600. I made an attempt to also figure out how to have like 4 values in a single structure, just computed at the same time. But due to my not the great understanding of Codal and RISC-V assembly, that failed. So I turned to software only optimizations, and that's saved me around 150 cycles. And what that was I merged the matrix multiplication with the vector addition, and I removed one of the loops we can see here at the start. Rows A is always 1, so that was unnecessary. So it added to the calculations in the indices. And the ReLU computation, as you can see here, it takes 2 arguments, A and B. But for our very specific use case, I could just have it happen in place. I have also attempted multiple other options for software optimizations. These were just the ones that actually had an effect on the cycles. Since the O3 flag already does a lot of optimization like loop unrolling and reordering of the loops. And yeah, the most promising one would have been figuring out how to do 4 multiplications in a single instructions. And I'm glad I got to figure that out in other people's presentations. Thank you for your attention.
Hey everyone, I'm Osman and I'm gonna present my solution for the hackathon. So what was the aim of the hackathon? It was to speed up a neural network. And you know what neural networks rely on? Matrix multiplication. So I tried everything. I tried to speed up matrix multiplication as much as I could. So let's inspect our base processor. It was an RV32i, which means it's a RISC-V 32-bit integer processor. So it had no multiplication instruction, but as you know, matrix multiplication also depends on multiplication. So so without any extensions, the result was around 20,000 cycles, and the processor used software emulation for multiplying. So when I added a multiply instruction, the cycle count got down to like around 3,500 cycles. And then I added a multiply and accumulate instruction. So you know, in matrix multiplication, MAC instruction is essential. It depends on the element-wise multiplication of columns and rows of vector and the matrix, and then accumulates the results into a register. So when I added the multiply and accumulate instruction, I saw that we got down to 2600 cycles around that. And then I went on with vectorization of the multiply and accumulate instruction. So what it allowed me to do is it allowed me to do multiple Mac operations at the same time. So we have a 32-bit processor, but our inputs were 8 bits, which means we can pack 4 of these to 32-bit, one 32-bit integer. So we could do 4 Mac operations at the same time. However, in the second layer, I had to pack only 2 numbers into one 32-bit integer because of the accumulation, the numbers exceeded 8-bit. So I had to use 16-bit integers for them. So one of the bottlenecks was like vector load instruction, like packing the integers into a vector integer. So for that purpose, I added a custom vector load instruction that packed 16-bit integers into one 32-bit integer, and it speeded up the packing operation. Another idea I had was using sparse matrix multiplication. Our inputs had like many zeros in it, and the sparse matrix multiplication skips 0 elements to save computational time. And at first, you need to find the non-zero elements of your number of non-zero elements of your vector, and then determine the indexes of non-zero elements, and then you only load the non-zero values into your vector registers, and then use these to do the multiplication. So you got rid of many of the operations. With that, I could do like Mac operation of 2 rows and columns at the same time. And another thing I did was, we were given like place for only 5 instructions, but I realized that we could use the destination register as input register as well. So if you write predetermined values to the destination register, you could have more than 5 instructions basically. So here you can see my instruction for like vectorized add and vector load operations. So results at the end, I got from almost 20,000 to 2,076. So it's down by almost 10%, almost 10 times. So for the problems and future work, as I said, overflowing problem was a huge bottleneck for me because it prevented me from using 8-bit integers in the second layer. And a future work that could be done is maybe enabling V vector standard extension of RISC-V. So it would be much faster, the load vectors and stuff, yeah. So I don't think we have time for questions, but thank you.
Hello. My title is actually pretty lame, but I did the same thing. And let's begin. I don't want to repeat what my friend said, but what our motivation is improving the given C code and hardware acceleration using custom instructions, working on 3 registers, using Codal architecture description language and Codesip Studio. My approach was accelerating the software side first, so that we know at the end what we should hardware accelerate. And yeah, I took a different approach, to be honest, and I decided to consider both O0 and O3 compile times, because I thought it's a reasonable demand to maybe somebody could want to get rid of the compiler optimization overhead. So for example, if something I did wasn't improving the O3 side, but improving the O0 side, I kept it, while giving preference to the O3 side, of course. And at the end, I had 2 final software side implementations, and I gave them names, Neon and Argon. Neon is the first one, and it has matrix multiplication improved, it has operations packed together, but sometime I also came across the idea that we could do the compression thing, compressed matrix operations, putting data into 8-bit space, just as some of my friends also did. And that Argon is Neon plus condensed matrix operations. But it's actually the same thing what you have also heard from some of my friends. And it's the idea I came up with very late, to be honest, instead of having 1,000 files in the downloads folder. Yeah, I implemented 8 custom instructions because we had place. Multiply, accumulate, unsigned division, shift left and OR, shift left and AND, biased ReLU, and for compressed matrix operations, compressed multiply and compressed multiply accumulate. And yeah, this is the result I got. Without no compiler optimization, the naive implementation is at 130,000, and my software improvements were at 95,000. With compiler optimization, we get to almost the same level for the both naive and neon implementations, because compiler optimization compensates for the software implementations I did, algorithm improvements I did. And when we also add the hardware acceleration on top of it, the model without compressed matrix multiplication gets to 2096, and the model with compressed matrix operations gets to 2416. I came across the same problem as my friend before, because on the second layer first, the multiplication result gets sometimes so big that it becomes impossible to store it in 8 bits. And that was also the biggest bottleneck I came across during the implementation. But yeah, this is the best result I got, and it means in hardware acceleration over the 22,000 number of around 90.5%. And I also have data for Arion power, because I figured out how to turn on the profiler. And yeah, we could expect to lose on area and lose on power consumption per cycle when we hardware accelerate between the first 2 naive and neon versions. But the thing is, I have seen that we gain actually nothing. At least I gained nothing by introducing custom compressed matrix operations, because it worsens the cycle time, it worsens the area, and it worsens the power usage per cycle. So I thought it's just not reasonable for matrices of the size we were given to and the program we were given to. It may be reasonable for matrices or programs much bigger, but for raw size, I thought it's not reasonable to implement it, and because of that, I left it. And yeah, this is the final result I got. For no compiler optimization, 26% of improvement. For compiler optimization, 2.5% improvement on the software side alone. On the hardware side alone, this time, these are not this is the software side alone, and this is the hardware side alone. This is not the final improvements. 88% for naive implementation by introducing those 8 custom instructions. 90.5% for the version without compressed matrix multiplication. And 89% for the version with compressed matrix operations. And the best cycle count I got at the end was 2096. Thank you very much.
Hey everyone, so I'm Jan, and we already heard a bit about this problem, so yep, I will jump right in. The idea was to either implement new instructions, optimize the source code, or maybe even just try to just already use inline assembly to optimize the cycle count. So the baseline was, as everyone else, 20,000 cycles, roughly. I think one thing I tried differently was in my current research work, I implemented a virtual prototype which can be used to trace and profile arbitrary RISC-V applications. So I thought it would be an interesting experiment to throw the neural network into the virtual prototype. So this is what I tried to do. This is not as easy as it seems here because I had to strip some of the syscalls from the executable because it used some coder specific stuff. So, for example, somewhere in the printf function calls. But with a few tricks, I managed to run the application on this virtual prototype, and doing this results in these generates a number of trees. These are basically execution trees, and just from looking at those, you may already can identify some of the functions here. I mean, you can see like 4 of the main functions which are executed very frequently, and on the right side, this is basically a tree for the and immediate instruction. And using the tool, I can basically then define what kind of sequence I'm looking for to maybe design an optimization. So looking at this tree, I find out that these 5 instructions make up more than 50% of total execution time. And those are basically the 5 instructions. And if we translate them, we can basically design a new instruction based on these previously 5 existing instructions. I mean, if we check actually where these 5 instructions occur most frequently, as you probably would have guessed, it's in the emulation of the integer multiplication, basically. So there's no surprise here. If we actually implement this new instruction, we go down to like 18,000 cycles, which is okay. But I mean, if we just look at the source code and just implement a single like multiply instruction, or we already go down to like 3,500. So I mean, it's a speed up, but for this small example, it's in many cases easy to just look at the source code and implement like some of the main functions, which I also did, like most of you already presented. Just implement the multiply, accumulate, and the redo function, which is used very frequently. The top 2 are basically the 2 instructions I devised based on the profiling I did previously, which somewhat reduced the cycle count, but obviously not as much as the multiply, accumulate instructions. I also found a number of different promising candidates for new instructions, but the main problem here was that most of them wrote to more than 1 register. So I couldn't really put that into a new instruction. But it tells me that the hardware would profit from being able to write to multiple registers, multiple addresses in one instruction, basically. So in total, if I combine all the new instructions, I get a very familiar number. I think most of you who didn't do much of the code optimization got a very similar number here. I also tried a bit of optimizing the source code. For example, because I already know all the parameters, I can drastically reduce the source code. The problem is, in every case, I was either as good as the compiler or worse. So I also tried a bit modifying the assembly directly, just rewriting the assembly, but I didn't have much time to go very in-depth into this. But yeah, I think that was everything I tried to optimize the hardware and the source code. Thank you very much.
Thanks. Hi, I'm Salar, and I think we can just jump in. I think I didn't do much different than anyone else, introducing 2 new instructions for multiply and multiply accumulate, and got it down to that 2,664. And that box should be bigger, but it basically goes to that multiply accumulate, right? And then I tried some C optimization before understanding from someone else here that the O3 is very aggressive and does the loop unrolling for you. I tried doing that first, and the compiler told me I cannot do this. But interestingly, when I do this, where I tell the unroll count, it goes up again. So I played against the compiler here, and I was very confused by that. And then I thought a bit more, maybe I can do it myself in some other places. And it was neither effective when I do it by hand in these, whether I do a unroll by 2 or unroll by 4. And it kept the number same. And then I had some more ideas. We have a limited amount of registers we can deal with, limited operations. Theoretically, we could exhaust the search space and generate all possible solutions and try them out if we have enough time. The possibility is to also study disassembly further, automatically, as we have seen, for example. And the add operation occurs a lot. There are sequences with AUIPC, but we would have to access the program counter. And I also saw that there's a lot of branches with instructions before and after, for example, the add instruction and those logic shift operations. I saw an optimization of that. And of course, we could inline the function calls, but I also believe now that the optimization 03 will do this for you as well, if it noticed this. And I think that's all I have, so thank you very much.
Okay, I think that's everybody. Please don't look at my desktop. So I'll just show the problems a bit more. I mean, you've heard of the CODASIP one and how people were coming up with solutions in the verification process. There were also a number of people that did the hardware with Renesas. I know a lot of people were excited to take that home, so I haven't heard how those worked out, but it looked like a great opportunity. And I'm just really grateful to be able to host this hackathon because the students really, I feel like, gained hand-on learning experience and access to tools that they wouldn't have had otherwise. Here are our judges who are back here looking all in their ambassador gear, I see. I love it. So big thanks. Yes, thank you, Daniel. So thank you so much to them. And thank you so much to CODASIP and Renesas for taking the time. This was created 5 weeks ago and really began to promote, and we moved really quickly. So if you are part of a RISC-V member organization and you're interested in participating in the future, please do let us know. We are going to be doing more of these hackathons. We're planning to do one at each RISC-V Summit. Not enough time to do it in China at this time, but we will be doing it at the North America Summit. And based on conversations I'm having here, it's possible that we'll do it both in person at RISC-V Summit and virtually simultaneously. So we really want to make sure that everyone in the community feels like they can be involved in these. And we're really excited to watch the progress of the students. In my mind, this is a great way for employers to take a look at how people's brains work and how they solve those problems. So if you have any feedback or questions or want to say anything, you can get me at learn@riscv.org or megan@riscv.org as well. So I don't know if people have questions for any of the presenters. If you do, we have a few minutes. So nothing specific? Yeah, I didn't get the presentation for the last one. Yeah. Yeah.
Sorry, Jan. One thing I didn't catch, did you have a multiply instruction or not? Okay, but you also added instructions to optimize the software routine for multiply.
So the first result was for just this instruction which optimized the emulation of the multiplication. I still kept it in after adding the multiply instruction. Of course, this one wouldn't be used anymore, but it was still used in like 170 places by the compiler. So for the first part, it still gave some optimization. But as you can see, the end result was the same. So in the end, I don't think it didn't give me much because it maybe replaced some other instruction I also used. But this, of course, the multiplication in this part would replace the part I found. I would have liked to iterate a bit more to throw the new binary into the virtual prototype again, but then I have to also update the virtual prototype of the new instructions, which takes time, which I didn't have. But yeah, this would be a nice iterative loop to then check again what I can find after implementing the multiply instruction.
Anything else from the judges? They look like they're deliberating. Well, thank you so much, everyone, for participating. I hope you found it as helpful as we hoped you would. And again, feel free to email me if you have any questions or ideas or want to participate in the future. Thank you.